Hello and welcome. We're going to take a look at PV diagrams. P and V are pressure and volume, and a PV diagram is essentially a chart where pressure is located on the y-axis and volume is located on the x-axis. One of the things that is useful about these is they're a visual way to track thermal processes, and you can actually get a lot of information off these diagrams. First of all being, if you have a point on a PV diagram and you know what the value of P and V are, you can use this to find temperature. Each spot on this graph corresponds to a particular temperature. That works out because of PV equals nRT. If the number of moles is constant, R is clearly a constant, you can actually read the pressure and volume off the graph. You can calculate the temperature. The actual distribution of temperatures on a PV diagram is not super easy to spot. There are lines that can be drawn along a PV diagram called isotherms. And isotherms have this funny curved look to them. Each one of these might correspond to a particular temperature. So you might have a 200 Kelvin, a 400 Kelvin, a 600 Kelvin. And the idea being that any point along any one of these lines has the same temperature. So that particular combination of pressure and volume at both of these points would be the same. The product would be the same. The reason they kind of have this inverse look to them is because, frankly, you're just saying P times V is a constant, and that leads to an inverse relationship. So that's what they kind of look like. Now, that can be very useful because if you know 2 points happen to be along an isotherm, you know that P times V is the same for both of those. Any process that moves in a direction from one isotherm to the next is an increase in temperature. So it doesn't matter how you do it. You can see there's many directions you could go to increase temperature along this line, but you would actually have to know that where the isotherms are. If you're moving up into the right, it's clear you're increasing temperature, but a move to the left could be somewhat of an increase in temperature if it's also up into the left. One that I know for sure will never be an increase in temperature would be a movement that would be down and to the left. That's only going to take you to a lower isotherm. Now, I think it's really important to look at the PV diagrams in terms of the processes that we talked about before. So let's start off with isobaric. And remember, isobaric stands for constant pressure. If you have a movement from one point to another on a PV graph and the line is horizontal, that's your constant pressure, but you do have a change in volume. In this case, work is being done. Remember, work equals pressure times change in volume, with a negative sign thrown out in front for fun purposes that I described in our previous video. Now, if I'm increasing the volume and the volume difference is positive, then this is negative work. If I were decreasing the volume, that would be positive work. So one way to look at that on the graph is that if the line moves to the right, you're talking about negative work. So this equals negative work, and a line that goes to the left would be positive work. That's an important thing for answering conceptual questions about these. If you can get that straight, you're going to do pretty good. And the way I do it, because I can't remember anything that is that binary, is I just remember that compressing a gas is putting work into it, and expanding a gas would be the opposite. If you were to actually calculate this, the origin is 0. The pressure that we're reading is, in a sense, a distance up along the y-axis, and the change in pressure, or volume, excuse me, is a distance along the x-axis, which means that the work being done can be thought of as the area underneath the curve. In this case, it's very easy to find because it's a rectangle. You just multiply height times width. In other cases, it's still true. It's just not necessarily as easy because you don't have this obvious, simple geometric shape. It is important to note that you can have different pathways getting from one point to another on a curve. So let's say I have point 1 here and point 2. Moving from point 1 to point 2, let's say along this pathway, is going to get you from one temperature to another. But let's say instead you move to the same spot along this pathway. You have the same initial temperature, you have the same final temperature, but what you don't have is the same amount of work. The work being done on the bottom pathway is the area under this curve, and I think it's clear to see that that area is smaller than the pathway taken on the higher path, the black path in this case. And so that's something to be careful of, and it's also something to that's good to know if you wind up in a situation where you're asked a conceptual question about this. Just remember, area under the curve equals the work done. Another process that we might look at would be an isochoric or isovolumetric. Now in this case, we might start at a particular pressure and move with constant volume to a different pressure. Now in this case, if you don't have a volume change, there is no work being done. But I think it's clear you could see that this could be a temperature change. So imagine if you had a cylinder of gas and you changed the pressure without changing the volume. That's probably an indication of an increase in temperature or decrease in temperature that's causing that to happen, assuming that no gas is coming or leaving. One other thing that we're going to encounter are cycles. So you could have a situation where you do a special set of pathways and kind of complete a cycle and wind up where you started. So let's say, for instance, we had point A, B, C, and D. And this is a very simple and probably not very realistic looking one, but that's okay. We like to start simple. And if you made a movement from A to B, which would be isobaric, and then made a movement from B to C, which would be isochoric, and then from C to D, which is also isobaric, and then back to where you started, another isochoric process, you've completed an entire cycle. You have done some manipulations of the gas and wound up at the same temperature where you started. Interestingly, in this case, even though you wind up back where you started, the net amount of work done is not zero. For instance, in the cases of the isobaric processes from A to B and C to D, those are both places where work got done. The work being done on the A to B path, first of all, is from left to right, so it's negative, and the work being done from C to D is positive. So first of all, they're not even the same sign, and second of all, I think it's clear to see that C to D, the height above the axis, is bigger, so it encompasses more area. And so you have some positive work being done from C to D and a lesser amount of negative work being done from A to B. Well, at the end of the day, what that means is that the actual net work being done is the area encased in the process. So this here is the area being enclosed. And one way you can think of whether this is positive or negative is to look at the top. If the top is positive, like it is in this case, the net work would be positive. If it were the other way around, it would be negative. But another cool way of looking at this is that counterclockwise traveling around there equals positive work, and clockwise would be negative work. The shapes don't have to be this pretty and uniform, and often they're not. A typical example would be a more realistic looking one where you might have something along these lines. That's clearly not a rectangle, but what is still true is that the area encased by this process is the net work being done, and in this case, because it's a counterclockwise motion when you go around your pathway, this is positive work. Now, we've talked about isobaric processes. We've talked about isochoric processes. Let's talk about isothermal processes. An isotherm is a line that follows a constant temperature. And I kind of showed you what those look like. They're this kind of inverse looking curves. Every point along this would be at the same temperature. And so any process that followed this from one point to another and went along the line would be an isothermic process. And what we would know, because the isothermic process is a constant temperature, that means a constant internal energy, which means that the work and the heat transfer are equal and opposite to each other. Also, we talked about adiabatic processes. Adiabatic processes look similar to isothermic processes, but they're steeper. And honestly, you're not going to be able to look at two lines and know which is which. Somebody's going to have to tell you that. That's not something that you can just look at and go, oh, that's so clearly an isotherm, or that's so clearly an adiabatic process. If you are told one or the other, then that's a whole other story. Remember, an adiabatic process is one in which the heat is equal to 0, and so our delta U is equal to the work done. Now, armed with this information, you should be able to attack your worksheet. I know I didn't do any very specific examples, but again, there's too many. And I'm hoping you were getting to the point now after a year and some of AP Physics that you can take the basic principles and apply them. And of course, if you're having trouble with that, you can refer to the online solutions or come to me for help. Though those of you out on the web probably can't, but there's a lot of good resources out here, and I hope that this is enough information to at least get you started.